Hi, this is Lecture 12, and in this lecture, we're talking about ripple-free deadbeat control. We're basically talking about control of sample data systems. In this approach, we're going to primarily focus on ripple-free deadbeat controls. And so, as you can see, there are a number of issues to be addressed under this particular topic. So, here's our basic control structure that we're concerned about. So we have our plant, we have our controller that we're looking at. The control output of the controller goes through the digital to analog converter that exits the computer. So all of this is in the computer. That exits the computer, goes into our system. The output of our system is sampled and through the analog to digital converter and goes into a controller. So in terms of what is given here, we're given a system and we're given a reference input. So here, R of S is the continuous time version as numerator and denominator. The discrete time version of R is R of Q, which is NR over DR. And so we have these two are obviously related to one another. You obtain this by taking the inverse Laplace transform of this, sampling, and then taking the Q transform. And so this model we've obtained either by first principles, getting the transfer function in continuous time, taking the H transform, or else obtaining this directly through system identification. So now we have a system. Now before we get into this, I need to review a few important concepts. First, the concept of a root. A polynomial is said to have a root at some value R0 if you evaluate the limit as q goes to R0 of f of q, if you get 0. That is the definition for a root. So notice that if you have a root, if f has a root at R0, then we can factor the polynomial this way. That should say q there. There, like that. So this is now a function of q, and if q is equal to R0, this term is 0. And so that's the important thing here, is that if we have a root at R0, then we can factor out the polynomial. We can factor that term out of the polynomial. Okay. If R0 is not a root, then if you evaluate the polynomial at R0, you get something that's not 0. And so we can divide by it. So that's the important thing here. So these are some important definitions or properties of polynomials. Next, we have the definition of coprime polynomials. Coprime is not a word you probably have used very often before. Two polynomials, f and g, are said to be coprime if they have no common roots. Or one way of saying that is, if R0 is a root of f, then R0 is not a root of g. Similarly, if R0 is a root of g, then f does not have a root at R0. So the two are coprime, no common roots. So if f and g, for example, correspond to the numerator and denominator of a rational function, this is basically the same as saying there's no pole zero cancellation. Okay, so that's another way of saying it. So this notion of a coprime, of two polynomials that are coprime, is very important. We're going to be using that concept quite a bit in all of this thing about the ripple-free deadbeat control. So, polynomial degree. So the degree of a polynomial is the highest power of q with a non-zero coefficient. So the degree of this polynomial, for example, is 2. The degree of this polynomial is 1. The degree of this constant is just 0. What's the degree of 0? I'll let you ponder that. If the degree of a constant is 0, then what's the degree of 0? It's actually kind of tricky. Now, we've talked about some basic controllers already. We've talked about an open loop control. We've talked about closed loop, simple closed loop. In the cases that we looked at, we were basically looking at continuous time controllers for our system. Okay? And there's a way to discretize such a controller. We saw that there are advantages and disadvantages to using open loop, to using a closed loop control like this, like a PID controller. there are advantages and disadvantages. We're assuming that because we're now looking at these more advanced controllers, that there's some limiting properties of these two controllers that make them not so worthwhile to use. If these are available to use, then it's probably a good idea to go ahead and use them and not go further. So I'm assuming now that our control problem is a little bit more complicated than what could be solved using either the open loop or the simple closed loop controllers we've been talking about. That brings us to the basic problem definition that we're going to be looking at here for the ripple-free control problem. So the ripple-free control problem basically has three main properties. The first property is that the closed loop system is internally stable. So that's obviously needed. We needed that in the other controller designs too. So if we started off with this open loop unstable system, we cannot use an open loop controller. It's just not possible. Also, if we have an unstable system, it's possible that using even a PID controller is not sufficient to stabilize it. And even if and it's possible to design controllers for systems that are stable in the sense of the transfer function, but with pole zero cancellations for poles that are in the right half plane. That's generally not a good plan, in which case the system is not internally stable. The transfer function, the overall closed loop transfer function, might look stable, but it's actually not internally stable. That is, there are signals that may be blowing up in the system, and so that's not good. So that's the first property. And we're going to look specifically in detail at why the ripple-free deadbeat controller is able to satisfy these conditions. Okay, turns out that other design techniques cannot satisfy these conditions. The second condition is that the error of the system, the difference between the reference signal that you're trying to track and the output, that must go exactly to 0 in a finite or fixed number of sampling periods. So after a certain number of sampling periods, boom, from that point on, the system is stable. Okay, I'm not so stable. The system is actually settled. It's exactly settled at that value. So this is an important property. And the last one is that the control signal itself settles to its final form in a finite number of steps. And we're going to see what the implications of each of these conditions is. Okay, but before we get into looking at the specific property, we have some basic assumptions we're going to make in this design problem. So the first assumption, the essential assumption, is that the reference input is a rational function. So the reference input and thus the discrete time version of that reference input, these are rational functions. Okay, so that is actually an important thing because we're going to actually need to come back later and look at this and see exactly what's needed to get true ripple-free tracking in the event that you have something other than, say, a step input, something simple like that. That's the first thing. So in other words, what this design approach that we're going to use is it's going to actually incorporate information about the tracking reference input into the controller design, and in doing so, it needs to know what that is, and in particular, it needs to be a polynomial over a polynomial. We're going to need those polynomials in order to solve the problem. So it turns out that we've actually made these assumptions in the previous controllers we've designed. So this is no more restrictive than anything we've done so far. So these are perfectly reasonable assumptions. But whenever you do have assumptions, it's always critical to ask, are they valid assumptions? Are they worthwhile assumptions? Are they reasonable assumptions? Okay, so these are important things. So these are very reasonable assumptions because this control design can accommodate many different types of signals. Okay, now again, we're not trying to solve every control problem in the book here, but we're trying to solve a wide range of control problems. And so by keeping things as general as possible, we're going to try to be able to solve a more wide class of control problems. So the second thing we're going to look at is second assumption is that NP and DP are coprime. That is, the numerator and denominator of the plant do not have no cancellations. So remember we talked about that. So there are no cancellations. So this condition here actually is very reasonable in the sense of if you go on later to into deeper control theory, you'll learn properties of controllability and observability. These properties basically say that the system must be controllable and observable. And so those are very reasonable assumptions for systems. The last condition is no transmission zero. Now what does that mean? Okay, what this implies in terms of our control problem is that the numerator of the plant and the denominator of the reference input are coprime. So the numerator of the plant must be coprime with respect to the plant's denominator, and it must be coprime with respect to the reference input denominator. Okay, so the transmission zero is very important. So what is a transmission zero? So a transmission zero is for the system. You're going to apply an input to the system. Okay, and the transmission zero basically is associated with the question, am I going to try to track a signal that I can actually track? Okay, that's basically the problem. So if you think of your transfer function as a filter, suppose you think of it that way, all right? And suppose your transfer function has a notch. That is, there's a frequency at which you get no output, zero output. Okay, now if you happen to apply as an input a sinusoid at that exact frequency, okay, that's a frequency at which your transfer function has zero output, and yet you apply a signal at that frequency. Well, you wouldn't expect your system to do very well in that case, right? So that would be an example of a transmission zero, where the notch in the system lines up with the signal you're trying to track. And so basically, this condition is very reasonable that there is no transmission zero. Basically, it's saying we're not trying to track a signal that our system cannot track. Okay, so that seems like a pretty reasonable assumption. Okay, in fact, that assumption is pretty much required to be able to control a system in any reasonable form. So anyway, you can actually relax some of these assumptions, but we're pretty much going to just stick with these assumptions. It keeps everything really straightforward. They're all very reasonable to begin with, so we're going to stick with these. Now, there are actually other assumptions that we're going to make. First of all, that the denominators dp and dr are monic. Okay, and again, we can always make that assumption. dp and dr are monic, which means that if you evaluate the polynomial at 0, it's equal to 1. Okay, so if that's not the case, then you can divide numerator and denominator through by whatever this value is, and you will get you will have this property. So the main thing here is that q itself is not a factor, or there is no root at 0 for either of these two polynomials. That's one of the key assumptions in all of this. Turns out that if you did have that, you can actually redefine the transfer function in a way that we will not get 0, or else you'll have a system that's not causal. So part of what this implies is that our system is actually causal, and so that's again very reasonable assumption. Also for our reference input, that it's also a very reasonable assumption that we're having causal input and a causal system. So this is a very reasonable assumption, causality. Second thing is that we're going to assume that our plant is strictly proper. Okay, that is, if we evaluate the numerator polynomial at q is equal to 0, we get 0. So this is actually a little bit different kind of property, and it turns out that not every system satisfies this property. But this is an important property that that's going to simplify things greatly for us, and so we're going to make this assumption. We could actually come back and relax this assumption. It will just make everything more complicated. And so for now, we're going to just start with this assumption. Okay, it's going to definitely simplify things, so we'll start here. Actually, this assumption is also reasonable because many systems have this property. Many systems have this property. So we're not stretching things too much to assume this. No degenerative sampling. We talked a little bit about degenerative sampling earlier when we talked about sample data. So the concept of degenerative sampling is that I'm not choosing a sampling period that's associated with the Nyquist frequency of the system, of any of the poles of the system. Okay, so and again, it's okay if I actually have aliasing. The important thing is that I do not have something exactly at that Nyquist frequency. Okay, that's the critical thing. So it turns out that this property is true for almost all sampling periods. That means there's only a fixed number of sampling periods, finite number of sampling periods. So in any interval, remember there's an infinite number of values. I can choose any value in there except maybe one, maybe two values. Any other values, any of the other infinite values I can choose. So this is not very restrictive to say this. So we're just assuming we're going to choose a reasonable sampling period for our system, something that just doesn't give, isn't at a Nyquist frequency, which is kind of a critical frequency. Right, so that's important. Now, as I mentioned here, our reference input is a rational function. Well, for the most part, we're going to assume rational functions like this, a step input. So here's a step input. It's a rational function. Here's a sinusoid. It's a rational function in Q. Okay, and so these are the kinds of functions we're going to look at. And there, as you can see, it's a rational. So notice for a fixed omega naught, for a fixed phase phi, and for a fixed sampling period, this is just a constant. This is just a constant. This is just a constant. And so we just have a constant polynomial over a polynomial. Okay, so we have that, and so these are common reference signals of the type we would use. So again, this is very reasonable that we would restrict our attention to these kinds of polynomials. Okay, so those are all the assumptions we're going to make. Now, what about our controller structure? Well, if you noticed in the controller structure, there were two inputs coming in. There's the reference input, and then there's the feedback input. Two inputs coming in, one input going out. And so this kind of a controller is called a 2-degree of freedom controller. Okay, so for a 2-degree of freedom controller, our control signal U is equal to controller 1 times the reference minus the controller 2 times the output of the system. And each of these transfer functions, C1 and C2, are a rational function, N1 over DC, N2 over DC. And here we can make the assumption that we have the same denominator for both N1 and N2. So it turns out we could choose different denominators if we want, but it turns out this does two things. One is it means we only have to solve for one polynomial between the two transfer functions. The other thing is that it makes implementation a lot easier. Okay, so this is what we're looking for in terms of our controller. So I don't know what N1, N2, and DC are yet. That's what I need to find through the controller design process. But that's what I'm looking for. I'm looking for polynomials N1, N2, and DC. So as we go through this, we're going to continually be looking for how to obtain those and what N1, N2, and DC would qualify as solutions to this. Okay, and again, we're looking for controllers that are proper with monic denominators. In particular, what that means is the monic denominator, actually the monic denominator, so the same one, as long as that's monic, pretty much this whole thing is, if this is a polynomial, this is a polynomial, and this is monic, the system will be proper and have it will be proper and have a monic denominator. In Simulink, our block diagram would look like this. So here's our controller. We can have N1 over DC, N2 over DC, and then our transfer function over our plant. So that's what the controller structure looks like. Okay, applying the 2-degree of freedom controller, we get the closed loop transfer function given by this expression. So this is the transfer function from the reference input R to the output Y. And how do we get that? Well, so this is R, this is Y, and so if I define this signal here to be, well, this is actually the control signal U. U is equal to C1 times R minus c2 times y, and y is equal to p times u. So I have those two equations. From those two equations, I can solve for y in terms of r. And when I do that, I get this expression. Okay, in terms of c and p, c1, c2, and p, the H transform of p. So this has numerator n1 over dc. This has numerator np over dp. This has transfer function n2 over nc. And so when we simplify this in terms of the polynomials, this is what I get. So there's my transfer function. So that's the transfer function from the reference to the output. I can define other transfer functions. So for example, I could define what's called the error transfer function. That's the transfer function from r to the error. So the error is r minus y. And so r minus y over r, that's the transfer function, right? R over r is 1, y over r, we have just solved for. So plugging that in here and simplifying all of this, I get this expression. Notice I have the exact same denominator as I had in the previous transfer function, which basically is saying that regardless of where we take the output from our transfer function, from our system, regardless of where we take the output, what we treat as the output, I'm having the same poles. Okay, I have the same poles. Finally, we have the control transfer function. The control transfer function is the transfer function from r to u. And so I can actually define that this way. It actually comes out to be c1 minus c2 times the closed loop transfer function, that is the transfer function y. And again, when I simplify all of this, I get down to this. So again, a polynomial over a polynomial, same denominator as I had before. So I can define these different transfer functions. Why do I want to define these different transfer functions? Because the output, the error, and the control signal are the main signals I want to look at when it comes to the performance of the system. How is the system performing? I want to be able to look at those three specific signals in evaluating the performance of the system. Okay, so those are the closed loop transfer functions. I've defined now the basic structure of the problem. And now I want to look at the basic requirements. So the first requirement was, remember, internal stability. So how do we achieve internal stability? Well, here's what is needed in order for the system to be internally stable. First of all, I can have no unstable poles or zeros canceled. Okay, so remember I mentioned that you can have pole zero cancellations. Well, you can, and the transfer function looks stable, but internally the system is not stable. Also, we have cancellations that may occur among stable poles and zeros. So we can have cancellations, but if we have cancellations, they need to occur among stable poles and zeros. The third condition is that causality must be maintained. And finally, the last condition is that the poles may be shifted, so they will not necessarily be canceled, they may be shifted. And so actually most of the time, this is actually going to be what we're going to do. We're going to shift the poles, not cancel. So if these conditions are satisfied, we will have internal stability. Okay, so cool. That's good to know. Second condition is the error goes to 0 in a finite number of steps. So remember that a discrete time signal that goes to 0 in a finite number of steps is called a finite settling signal. And so when we looked at the properties of the Q transform, that was an important property that we looked at, finite settling. So a finite settling signal in the Q domain basically is a polynomial in Q, not a rational function, not a numerator over denominator, it's just the numerator. Okay, so a finite settling signal that settles to 0. So we also talked about finite settling signals that don't settle to 0. It settles, but not to 0, so to some other value. So one that settles to 0 is actually a polynomial. Now, this concept of a finite settling signal is something that actually cannot happen in continuous time systems. So if you recall, whenever you have the inverse Laplace transform of a function, it's going to be e to the minus something t. So it asymptotically goes to 0, but it doesn't go to 0 exactly in a finite time. Okay, it asymptotically, which means mathematically speaking, it never actually gets there. Practically speaking, it may get there fairly quickly, but here, notice that it goes exactly to 0 in a finite number of steps. That's critical. So what does it mean for the error to go to 0? Well, here's the error. We have the error transfer function times the input. So that gives the actual error signal. Now, what's needed for this signal to be just a polynomial? That's the question. So here's P subscript E. We found that expression earlier. Here's the reference input. Okay, and somehow all of this mess needs to come out to be a polynomial. So notice this term here does not look like it looks like I have plenty of stuff in the denominator. So how am I going to get this to be only a polynomial? That's the mystery. Okay, well, here's the mystery revealed, the solution to this mystery. So in order to make the error polynomial, a couple things need to happen. First of all, the numerator must cancel with dr. Wait a minute. I thought we couldn't cancel stuff. And especially, for example, dr. Suppose dr is a step input. That has a pole on the unit circle, right? On the unit circle. If it's on the unit circle, then that's not in the stability region, which is outside the unit circle. So if that means I'm canceling something unstable. Okay, so now this is important. We're gonna actually see this. It turns out the cancellation here is actually needed in order to get proper tracking. And it's not a problem that you're canceling this in this case because, well, as long as we're not trying to track a signal that's blowing up. Okay? If we're tracking a signal that's persistent, like a step input, or a signal that's a sinusoid that just has constant amplitude but doesn't decay to 0, then we're good. So actually that's okay. That cancellation is actually an okay cancellation. Notice that we're not canceling anything inside the plant. The cancellation occurs outside the plant, right? This is outside the plant. This is being applied outside. So the unstable part is actually being applied outside the system, right? It's being applied to the system, but it's being applied from outside the system. So whatever's out there is what has to generate this signal, and so that's the thing that we need to worry about. So in here, in our system that's not affecting the poles of our system. That's only affecting the zeros, and that's actually okay. So I hope you understand. That's okay to do. We need to cancel. So somehow all of this mess has to cancel that, okay? Because again, all of this has to become a polynomial, which means that has to go away somehow, all right? Now, what about this guy? Well, it turns out we can make this whole thing a polynomial if the remainder of the denominator, that is all of this stuff, is a constant. If it's a constant, that's an interesting thought. How would we make that into a constant? Well, we'll come back and look at that. So basically, making the numerator cancel, dr, we must have all of this is equal to dr times something. Okay, so this is a polynomial. In general, the order of this polynomial will be greater than the order of dr. And so what this is saying is all of this stuff must be equal to dr times some other polynomial q1. Okay, so that's the only way this can cancel with that, is if all of this stuff has dr as a factor and then some other polynomial left over as the remaining factor. Okay, so we need that. Second thing is this. In order for this to be a constant, we can set it just equal to 1. Well, why 1? What if it's some other constant? Well, it turns out if it's some other constant, well, we can divide through by whatever that constant value is and just get 1. So without loss of generality, we need to find actually the polynomial n2 and dc to make this equation satisfied. Okay, to make this equation satisfied. Now, so that's the kicker, is that we need that to be satisfied. Okay. Now, suppose this is satisfied. We had the other condition about dr factoring the numerator. So if I look at the numerator, notice that all this stuff is in fact this stuff, which is just 1. That means 1 minus this is equal to, and we saw dr times q1. If we rearrange that equation, we actually get this equation. Okay, so notice these two equations look very similar to one another. They both have NP in them. Okay, and they're both polynomial equations that are equal to 1. Okay, so if we now make if we set these two things to be equal to 1, the error becomes this polynomial. Okay, that is, this becomes dr times q1. That's what the numerator becomes. This becomes 1, and so the whole thing, so the dr is going to cancel. This is just 1, and so I'm just left with q1 times nr, and that's just a polynomial. Cool. So we have that's what we were looking for. So we got it. And in order to do that, we require that our controller polynomials, n1, n2, and dc, satisfy these two equations for some other polynomial q1. Okay, so that's what we need to do. So basically, setting this equal to 1, the error becomes a polynomial. And again, we made the poles somehow. So remember, this was the denominator of the transfer function. And somehow we made it equal to 1, which meant the poles went away. Went away. Where did the poles go? Okay, so notice here, I'm not canceling anything. I'm choosing n2 and dc to make all of this equal just to the number 1. Okay, and so where did the poles for the system go? And here's a hint: the poles of the system has just as many poles as it did before. So even though this is equal to 1, which was in the denominator, my system still has the same number of poles, which is crazy. We didn't cancel the poles. So what happened to them? So in our transfer function, with this as the denominator, now it's just equal to 1, we have our transfer function is a polynomial. So where are the poles of a polynomial? Where are the poles of a polynomial? We've actually looked at this question in class before. And so basically the poles of a polynomial are all out at infinity. So remember, the pole is when you take the limit as q goes to that value, your function goes to infinity. Well, if you have a polynomial and q goes to infinity, the polynomial goes to infinity. Okay, so it turns out that all the poles are at infinity. Poles at infinity are outside the unit circle. Okay, so the region of stability in the q domain is outside the unit circle. So those poles are outside the unit circle. They're as stable as they can get. So have we made the system stable? Yes, we've made the system stable. In fact, we've put the poles actually out at infinity. They're as stable as they can get. So we've really done a good thing here. So that's the second basic requirement. The third basic requirement is that the control signal settles. Now, it may not be obvious to you why this needs to be the case, but if we use the given design equations, here's our control signal. Notice that the denominator dr appears as the denominator of our control signal. Okay, so this is the final settled form of the control signal. That is, for example, if you have a step input that you're applying, well, the denominator of that step input basically requires that our control signal, when it's after everything is settled, our control signal be a constant. Okay, what this is saying is, if our input, for example, is a sinusoid, then what this is saying is that our system is going to, our control signal is going to settle to a sinusoid. So in other words, in order for the output of the system to be a sinusoid, the input of the system needs to be the input needs to be a sinusoid. It has to have the right magnitude and phase over here in order to get the right, remember the inversion principle? We need to have the right magnitude and phase in order to get the right magnitude and phase out. And so that is, that's what we need to do in order to to get this. And so this is the form. And so we can see that, in fact, this final settle form of the signal is going to settle to the final form in a finite number of steps. It has the right denominator. So where the problem would lie is if you had additional terms here in the denominator that can take longer to settle. But we don't have those here. Okay? We don't have those additional terms, and so this won't take longer to settle. So in general, remember, in discrete time, a continuous time system, for example, if you have a pole at 2, basically that corresponds to a geometric sequence that each time decreases by half each time. And so notice that, like the exponential, it eventually goes to 0, but it never mathematically goes to 0. So that's the kind of thing we could have here in terms of poles, but we don't because of the assumptions and the design equations that we have chosen. Okay, so we're good. All right, so just to back up, internal stability, the error goes to 0 in a finite number of steps, the deadbeat property. The control signal settles to its final form in a finite number of steps. That's the ripple-free property. So these are the properties that we end up having. So the question now says, what happens if, for example, internal stability is not satisfied? So we start with this unstable system. Here's the H transform of it. And let's assume we assume that the controller C1 and C2 are equal, and we let them take this form. Okay, so notice that this 0 of the transfer of the controller cancels with this 0 of the plant. Okay, so you can go through and show that you will get a deadbeat system, but it won't be a ripple-free deadbeat system. Okay, so if you were to look at the output of the system, this is actually what you'd get. So notice that for a step input, it goes up and it settles at 1. Okay, and it stays at 1 for a long time, but then eventually it blows up. Okay, so, and if you look at the control signal while all of that's going on, the control signal does something and then it settles and it stays at this value even though the output is blowing up. So it's like this. It's like the controller knows nothing about the system blowing up, even though we're applying feedback. So this is what happens when you have an unstable cancellation occurring. And even though we know exactly what the value is of that pole, you just get it when you have an unstable cancellation. It's generally going to lead to blowing up. Okay, so that's the issue of internal stability. The internal stability requires we have no unstable cancellations, and this is the kind of thing that happens if you have an unstable cancellation in your controller. So what happens if the control does not achieve its final form? So here is our plant. Here is our here it is in the Q domain. I'm going to choose this controller. Again, here notice that this pole is stable, and I'm going to cancel it with this 0 of my controller, and I'm going to choose the values of A and B according to these formulas. Okay, and so that's the same A and B. So notice I'm canceling these zeros, canceling these poles. Notice it's stable, so it should be okay, right? Stable cancellations. Okay, so but if you go through and show, if you go through and simulate the system with this, this is the response we get. The blue dots are the response of the system in continuous time. Okay, discrete time. Those are the discrete time values. Those are the values we get at the sampling instance. So in the discrete time, the system looks like it's stable, and it looks like it's settled at this point, right? But if you actually look at the continuous time signal, you can see that basically you've set yourself up to do aliasing. Okay, and the control signal has not settled to its final form. The control signal should settle to a constant. But notice it hasn't. It's got this oscillating sequence that's decaying, but it's stable. That is, it's decaying, but it's not settled. Okay, it should have settled here, and it didn't settle here. Okay, so that is a consequence of canceling zeros in the transfer function. So in general, basically what we don't want to do is actually do any cancellations. Okay, inside the loop. We can do the cancellation of the reference input. Remember, we looked at the reference input and the reference input and compared it with the numerator. That cancellation was okay. This is stuff that's happening inside. Okay, so basically, if the closed loop system is internal, if the if these conditions are not satisfied, if the closed-loop system is not internally stable, it blows up. If the error of the system does not go to 0 in a finite number of steps, the system is not deadbeat. If the control signal does not settle into its final form in a finite number of steps, then the system has ripple. So we've seen examples of all of these kinds of things and how they're affected. So if the basic conditions are not satisfied, that is, if the closed-loop system is not internally stable, it can be caused by unstable pole zero cancellations in the loop. If the control signal does not settle to its final form, it's caused by the controller zeros being canceled in the loop. So the bottom line is that cancellations in the loop are not good. Cancellations in the loop are not good. Now the equations, the design equations we've introduced are called Diophantine equations. They actually have a name, Diophantine equations. And it turns out that the Diophantine equations give solutions that don't cancel. Cancellations outside the loop can actually be helpful. So we've talked about that a little bit. So, but the Diophantine equations actually give us solutions that don't cancel. They shift. Okay. So the solution of the ripple-free deadbeat control problem boils down to the solution of two Diophantine equations. So here are the two Diophantine equations. These are, each equation has two polynomial unknowns. And if a solution exists to, for example, to this equation, then an infinite number of solutions exist. That's pretty cool. And that's actually going to be an important property that we're going to use in designing controllers. So we're going to choose among those infinite number of solutions, we're going to choose ones that give us good performance or robustness. And so we have these two equations to work with. Okay, so each of these equations is a Diophantine equation. So what's the deal with Diophantine equations? What do we do with the Diophantine equation? Whoa. Okay. Well, here we are. We're talking about Diophantine equations. Somehow I managed to change clothes. Anyway, Diophantine equations. So what's the deal with Diophantine equations? So here we're going to assume that we have the polynomials NA and DA as so remember we have two different Diophantine equations we're working with, each with a numerator term and a denominator that are known polynomials. And we want to find a solution to the Diophantine equation, an exact solution. So NA and DA appear in here. We're going to have an NX and a DX. Those are the solution polynomials, such that all of this is equal to 1. Well, it turns out that a solution to this type of equation exists if and only if the original polynomials that were given are coprime. Okay? If and only if. That means if these are coprime, then a solution exists. Or the other way, if a solution exists, that means these two are coprime. So that actually goes both ways. But the important thing is we start off with these guys being coprime, and we know that a solution exists. So in our problem, we actually have two equations. And so this set of equations has a solution if and only if NP and DP are coprime, NP and DR are coprime. So what do these actually mean? NP and DR coprime means no transmission zero. Well, we know that we needed that already, right? So that's a given, or rather that was one of our important assumptions that we made. NP and DP being coprime, that means no pole zero cancellations. Again, we already made that as an assumption. So between the two, we're good. We're good. So that means a solution to our control design problem exists. Sweet. Yes. All right. So given the polynomials then, how would we actually compute or calculate solutions to this equation for a given NA and DA? We're looking for a solution to this equation. So if we take this equation and divide through by NA and DA, so notice that when we divide by those two terms, in this term we just end up with DA in the denominator. The NA cancels. In this term, the DA cancels, leaving just NA, and then over here we have 1 over NADA. So now what is this actually saying to us? This is saying if I take this expression here and do partial fractions, okay, so these have roots, I do partial fractions of this term, and I group the terms that involve the denominator roots and the term that involve the numerator roots, so that I have, so again, I group these terms. Then whatever I get in the top is going to be nx, whatever I get in the bottom is going to be dx. So this can be solved using partial fractions. So by way of example, here I have a function, na, in this case np and dp, and we have this reference. We're going to track a step input. So first of all, note that np and dp are coprime, right? So that is, there's no common factor between the numerator and denominator. If I look now at the numerator here and the denominator here, that is also coprime. I don't have a root, a common root between this polynomial and this polynomial. So my conditions are satisfied, I'm good to go, and now I'm going to try to solve the Diophantine equations. So for the first Diophantine equations, I have 1 over np dr. So all of that, this is np dr here. When we do a full partial fraction expansion, this is the full partial fraction expansion. So notice that I have these two terms are the roots associated with np, then this is associated with dr. So when I combine these two terms together and I actually make the denominator equal to np, that is, I multiply by 2, which means I multiply both numerator and denominator through by 2, I get this expression, and then this one just comes right down, it's just a single term. And so all of this, all of this quantity is Q1. All of this is N1, according to our the one Diophantine equation. To the second Diophantine equation, 1 over NP dP, I do the same kind of thing. So here's NP, here's dP. When I do a full partial fraction, I get this. When I collect these terms together and make sure I have a 2 in the denominator, that is by multiplying the numerator through by 2, I get this expression. Collecting the terms for this, notice I don't have to do anything special in this case. That's not correct. Boom! There we go. Okay, this is what we should have had. That is, these two denominator terms, when you combine these, I should have that in the denominator instead. So this is what we get when we combine these two terms, and so this quantity here on top is NC. This quantity here on top is N2, and so we have a solution to that Diophantine equation. This is the second Diophantine equation. So we're good. We have solutions to all 4 Diophantine equations, and in fact, these are the minimum order solutions. Okay, we have the minimum order solutions. Okay, so it turns out that if a solution to a Diophantine equation exists, then it turns out there's an infinite number of solutions to that same equation. And to see that, well, so that's true, and it turns out the solution we find using the partial fraction expansion is that minimum order solution. The minimum order solution is a solution such that the degree of this is less than the degree of this, and the degree of this is less than the degree of that. Okay, so these two degree terms are known. These two are unknowns have the degrees that satisfy this. And generally speaking, even though it says this degree is less than that, it's usually equal to this degree minus 1. Similarly, this is dx has degree equal to this minus 1. And it turns out that the minimum order solution is unique. There's only one minimum. So even though there are an infinite number of solutions, the minimum order solution is unique. There's only one minimum order solution. So if we compute a solution now to this equation, for example, using partial fractions, it turns out that when you use partial fractions, the degree of this will be less than the degree of that, and similarly, the degree of this will be less than the degree of that. So these conditions are automatic, so they automatically come to pass. So that's cool. So in our problem, we need the 4 polynomials. And so there are 4 minimum order solutions, and they satisfy these 2 equations, and they satisfy these degree conditions. Okay, so that's what we're looking for in terms of our minimum order solution, the minimum order solution to the Diophantine equations. So that's what we need, and it turns out we can calculate them. in MATLAB, we can use the command I've created called doff2. In doff2, you pass it np, dr, and dp, and it computes the minimum order solutions to these two Diophantine equations. Okay, so we're good. We can calculate these things. Sweet. Next, we move on to talking about the general solutions of the Diophantine equations. That is, all solutions to the control problem can be expressed in terms of free polynomials, v1 and v2, where n1 and q1 can be written like this. Notice they are functions of the minimum order solution. n2 and dc can be written this way, and again, these are functions of the minimum order solution. These two terms are dependent on the value v1, the unknown, and this is dependent on the value v2. And again, any polynomial, v1 and v2, in these equations will still allow the Diophantine equations to have their solution. So it doesn't matter what these guys are, we will automatically get a solution. So this shows that we have an infinite number of solutions. So, and in fact, even if v1 is 0, notice that if v1 is 0, we get back to our minimum order solution. When v1 is anything else but 0, we will get something in general of higher degree. In fact, if you recall the definition or the degree condition on n1, the degree of n1 min was less than the degree of dr. And so we see that if v1 is a constant, for example, this polynomial now has degree equal to the degree of dr, which is greater than the degree of n1 min. So we can see that if v1 is anything that is not 0, this will have a degree greater than the degree of this. So, and similarly, we will get those same kind of conditions here and here. So now here I mentioned performance and robustness. Turns out these two Diophantine equations we will find that they can be used to characterize performance quantities. These two Diophantine equations will characterize robustness, and associated with these two, I have a unique unknown that is v1. Here I have a unique unknown that is v2. So by appropriate choice of v1, we can obtain performance. By appropriate choice of v2, we can obtain robustness. Now, how do I know that these are actually solutions? That's a good question indeed. Well, the way to find out is plug it in. So I'm going to plug in n1 and q1, for example. So here's n1 min minus dr v1. And here I'm going to plug in q1. Okay, and so we notice here I have np dr v1. Here I have dr np v1. This has a negative sign, this has a positive sign, so those two guys cancel. And I get back to the minimum order solution, which is indeed a solution. So that shows that this is equal to 1. That means it's a solution to the equation. Similarly with the second Diophantine equation. So basically, by adding these extra terms, notice that I've added the correct coefficient so that when I add these two terms together, those terms cancel, and I'm left again with the minimum order solution. So this is the general. This shows that those two solutions, those general solutions, are indeed solutions to the Diophantine equations. So how do we solve them? Well, first we start with the minimum order solution. Then we extend the order of the solution to obtain unknowns. Okay, and if we have a problem that can be set up then as a linear algebra problem in those unknowns, then we can use tools like the least squares problem, least squares tool. Actually, there's going to be a more powerful tool that we're going to be using in general called a quadratic program, and we'll see that when we get to the performance issues. So back to the original control problem. In the original control problem, we had this setup. So this is looking at it only in discrete time. I have my plant, I have my controller 1 and controller 2, and these are the polynomials associated with all of that. Remember, we were looking at these properties for the ripple-free deadbeat, that is internal stability. That's the first property. Second property is the error goes to 0 in a finite number of steps. That's the deadbeat property. And the control signal settles to its final form in a finite number of steps. That's the ripple-free property. So we had these three properties that we were looking at. So the ripple-free deadbeat control problem can be solved if and only if NP is coprime with both dr and dp. In this case, any of the solutions of the Diophantine equations will solve the problem. So remember, there's an infinite number of solutions, and that will solve the problem. Actually, that should say dr. Okay, there we go. Actually, that should say dc, not dr. So these are the Diophantine equations. Any solutions of these Diophantine equations will solve the problem. So notice that in terms of n1 and q1, I have the variable v1 that I can vary, and it doesn't matter if what v1 is in order to solve this equation. So they're independent. I have two independent unknowns that I can vary to solve the problem, or rather to manipulate the problem to do other things besides just the ripple-free deadbeat. So this will do the ripple-free deadbeat. Okay, it'll settle and finite number of steps. It'll exactly settle and so forth. No ripple. Okay, so that's awesome. Now the question is, what else can I do besides just that basic problem? Okay, so that's an important thing. So in order to answer that question, that's where we come to the issue of performance and robustness. And we'll be talking about these more in the future. So another thing we want to look at now is that remember we formed the transfer functions py, pe, and pu. So the py was the transfer function from r to y. This is the transfer function from r to e. And this is the transfer function from r to u. And because of the way the Diophantine equation works, each of these transfer functions ends up being just a polynomial. So we have a simple way of representing each of these transfer functions. And thus, when we look at the signals, so these are the transfer functions, for example, from r to y. Now, when we actually apply r to the system, we get these signals, y, e, and r. We can look at them explicitly. And so notice that in this case, I get this as a function of dr in the denominator. So this actually has poles. And so the poles of the output signal are the poles of the reference signal. And so so basically in terms of how this all comes to pass is that this numerator has been designed, or it will be designed, and actually according to the ripple-free property is designed so that this signal actually tracks the reference that we have. Notice nr and dr actually appear explicitly in here. N1 is our solution to our Diophantine equation, and it can be written in terms of n-min, and it turns out that it also is a function of dr, so the dr cancels. So I have this term that is, you can think of it as our minimum order solution, and then we have this additional response term that it can be used, that is a function of v1 that can vary the response. Similarly, I can write e this way, and in this case, remember, it's just a polynomial. The dr term canceled, and so again, I have this as just a polynomial. So this is the minimum order response, and then this is the response that I can vary by appropriate choice of v1. Similarly, the control signal is written by this, and I can expand it out this way, and it also, I can write this, this is my minimum order control solution, and then this, it can be varied by these terms here. So if you look at the overall response, each of these terms has a polynomial at the end. So the polynomial is a finite settling signal. Actually, it's a signal of compact support, and because of that, this term only affects a finite number of values in the transient response. So remember, when you have the response of a system, you have what's called a transient response, then you have the steady state response. So these terms only affect the transient response, and as a result, these are excellent things that we can use to work with the performance of the system, because the performance is primarily concerned with the transient response. So when you apply a step input, what kind of overshoot are you getting? What kind of settling time are you getting? And so forth. Okay, and those are all transient response issues. The steady state, once it settles, that's where we want it to be, And actually, that's already taken care of by the ripple-free deadbeat property. It's going to settle exactly where we want it to settle. If it's a step input, it's going to settle at the right value. If it's a sinusoid, it's going to lock onto that sinusoid and track that sinusoid. And so we have that result. And so the polynomial values here can now be used to modify what it would be the minimum order solution in each of these signals. Okay, so these are the main signals that I want to look at in evaluating the performance of the system. So what about a step input? So the step input is a very common kind of input. It's the kind of input we use, for example, with the PID controller and so forth. And so do we get any simplification if we know that we're going to apply this to a step input? And it turns out, yes, we actually do get a significant simplification. Let's take a look. So if you recall, in the Diophantine equation, it's only the first Diophantine equation, the one that involves dr. And so it's only the first Diophantine equation that depends on the input. So the second Diophantine equation is the same regardless of what signal you're tracking. Okay, so it's only the first Diophantine equation that determines the performance. And so in this case, for the minimum order solution, this is what we have. This is dr. So np n1 dr times q1. We have this. And notice that this must hold this. We have this equation. That means all of this stuff must be equal to 1 for all values of q. In particular, it must hold at q equals 1. So when q is equal to 1, this term goes away. And n1 min of q is equal to just, it's given by this expression. So notice n1 min needs to satisfy this condition. It needs to be the degree of n1 min must be less than the degree of dr. But this is dr, and that has degree equal 1. That means the degree of n1 min is 0. That means it's a constant. And here's the constant value, 1 over np at 1. So we know exactly what n1 min is going to be, and we don't have to do all that other partial fraction expansion to solve this. We have the solution already. It's np, the numerator of the plant evaluated at 1, the inverse of that. Okay, so there's you can see kind of some of the inversion principle going on here. But again, it's just a scalar value. It's a numeric value. It's just a constant. So sweet. And then, so since I now know this quantity, I can now solve this equation for q1 min, and this is what I get. And notice, even though I have this in the denominator, this is actually a polynomial. How do we know it's a polynomial? Well, remember, in the event, incidentally, how do I know that this is not 0? How do I know that this is not, and how do I know that np1, I can actually divide by it? How do I know? Ooh. Well, it turns out that because np must be coprime with dr, notice that dr has a root at q equals 1. Therefore, np cannot have a root at q equals 1, or else we don't have the coprime. As a result, we know that we can always divide by this. Okay, so that's cool. So back over here now, what happens when we let q equal 1 in this expression? Well, we have 1 minus np1 over np1, which is, this is 1. 1 minus 1 is 0. So that means this has a root at 1 minus q. Therefore, the 1 minus q actually cancels with the numerator. Now, this is in general maybe a complicated polynomial. Depends on the order of np, right? But that polynomial will always have 1 minus q as a factor. So this is actually a polynomial even though it's not obvious. Even though it's not obvious, this is actually a polynomial. Sweet. Okay, so we have now have an exact formula for the solution of n1 min and q1 min when we apply a step input. Okay, when we apply a step input. So that's really important. If we look at the error signal now, applying the solution to the system, we see the error signal is just q1 min. in the minimum order case. Okay, and so the degree of E1 of E is equal to the degree of Q1 min, which is now the degree of NP minus 1. Okay, so this comes from the Diophantine equation, this degree condition. And so basically this says that the system will track a STEM input and settle in a minimum of the degree of NP minus 1 steps. So this tells us exactly how long it's going to take for the system to settle. The system will settle ripple-free in that many number of steps. So it's a fixed number of steps, and we know exactly how many steps there are. So, cool. Okay, so let's look at just a specific example. I have this transfer function, and notice I don't even know what the coefficients A1, A2, B1, and B2 are. This is a general second-order system, and I'm going to apply the system with a step input. I can go through and show now N1 min is given by this expression, 1 over NP of 1. So here's NP, evaluating that when Q is equal to 1, I get this expression. And again, that's just a constant. Q1 min is given by this expression. We know what NP is, it's all that stuff. Divide by NP of 1, so this is what I get. And when I go through and do polynomial division in all of this, I get this expression. Okay, I get this expression. So Q1 min, in this case, it's actually only a function of B2. It's not a function of B1. But I have an exact expression for this. So notice the B1's canceled here. The 1 plus B2 in the denominator remains. And anyway, this is what I get when I do the polynomial division here. So this is a first-order polynomial because the numerator was a second-order polynomial, and I know exactly what it is. So I can solve that equation. Now the other Diophantine equation that involves NP and DP, well, that's something else. It's more complicated to solve for, but again, using partial fractions, we can solve it. So this now is the very beginning of the ripple-free deadbeat control problem. We've looked at what's required in order to solve this, in order to examine this problem, and now we actually have tools to begin to look at some of the important issues like performance and robustness. So again, we're going beyond what we could do with the PID controller or the static open loop controller, and so now we see we can stabilize the system, and we can have the tracking we want, and we can have that ripple-free property. That is, it exactly settles in a fixed number of steps. So, thanks for watching.